Hey everyone, welcome back to our channel. Today we're going to talk about the physics past paper 2 variant 2-3 from the October-November 2024 series. So let's get into the paper. Question number 1. Define acceleration. So this definition is very straightforward. It's basically just rate of change of velocity with respect to time. Okay. A small aircraft is flying horizontally at a speed of 42 meters per second at a height 63 meters above horizontal ground as shown in figure 1.1. The aircraft drops a small parcel. Parcel is released from the aircraft at the instant shown in figure 1.1. Air resistance is negligible. On figure 1.1, draw a line to show the path of the parcel as it falls from the aircraft to the ground. So basically this is a projectile motion, so it has some horizontal velocity and it will gain velocity as it moves forward. So it will be, somewhat like this. Okay. Calculate the time taken from the instant of release to the instant the parcel reaches the ground. So basically we will consider the vertical displacement. So vertical displacement is 63 meters. For this case you can say that this positive direction is downwards. If you take upwards direction to be positive, then you will take it at minus 63. But since the motion is just strictly downwards, so you can keep it simple. And initial velocity is 0, so we have we need the time, So S is equal to ut plus half at squared. So 63 equals to vertical velocity is 0 plus half times by 9.81 times by t squared. So t squared would be 2 times by 63 divided by 9.81. So basically square root of 2 times by 63 divided by 9.81. So you will get 3.583. So basically 3.6. So right. 63 meters. Okay, alright. Calculate the vertical component of the velocity of the parcel immediately before it reaches the ground. So basically we need the vertical velocity. We can use 2as v squared minus u squared. You can use the time parameter also because we know the time now. So for example, let's see both of the ways and see whether we get the right answer, same answer or not. So v squared would be equal to 2as plus u squared, 2 times by 63 times by 9.81 plus 0. So square root of 2 times by 63 times by 9.81, 35.157, let's call it 8. Let's see from over here. So u is 0 plus 9.81 times by the time period that we had was 3.6. So let's see, 9.81 times by 3.6, roughly 3.3 also. 35.3. Now had we used the slightly more accurate one, let's see, 2 times by 63 divided by 9.81, we would have gotten 35.157 also. So either way, that's perfectly fine. This would be slightly more better answer, 35 meters per second. Determine the speed at which the parcel reaches the ground. So remember, when it hits the ground, it has the vertical component of velocity also and the horizontal one. So horizontal one remains the same as 42, and just before it hits the ground it has 35 meters per second also. So magnitude of speed would be 35 squared plus 42 squared whole under root. So 35 squared plus 42 squared equals 54.6, so roughly 55 meters per second. And that's the first question. Moving on to the next one. Question number 2. State the principle of conservation of momentum. Now, this is also a very frequently examined question. So remember, there's an important assumption in this. It's that there are no external forces, or the system of bodies are isolated system. Okay, so principle of conservation of momentum states that total momentum of an isolated system of interacting bodies or objects remains constant. You can also say that the total momentum of interacting bodies remains constant when no external forces are acting. When no external forces are acting. So the alternative phrasing actually comes from the isolated system and no external forces acting. Okay. A ball X has mass 240 grams and moves in a straight line along a horizontal frictionless surface with an initial speed of 16 meters per second. Okay. The ball collides with a stationary ball Y that has a mass 480 grams. After the collision, ball X is stationary as shown. Right. Okay. Show that the speed v of the ball Y after the collision is this. Okay, so we will use the principle of conservation of momentum. So mx ux plus my uy equals to mx vx plus my vy. So remember, uy is 0, ux is 16. We need to keep direction one direction positive. Let's keep that towards the right positive. Vx is now 0 and Vy is just simply V. And M, this is 240 grams. So ball X 240. So you see masses are on both sides in grams. So we will have to multiply 10 raised to power minus 3 for all of them, so we can forego that also. So that won't change the mechanics. So all of these masses are in grams, so the ratio would be the same. Times by 16 plus 0, because uy is 0. Now this one is 0 plus 480 times by v. So V would be 240 times by 16 divided by 480. So 16, basically 240 divided by 480 is just 1/2, and 16 divided by 2 is 8 meters per second. Calculate the change in total kinetic energy of the balls due to the collision. Okay, so EK before and EK after. So EK before is half. Now we need the kilograms. 240 10 raised to power minus 3. Velocity was 16 whole squared plus 0. And now we have half 480 times by 10 raised to power minus 3 and 8 squared. So let's figure this out. So 0.5 times by 240 times by 10 raised to power minus 3 times by 16 whole squared. It is 30.72. And the next one is 480 and 8 squared. So we get 15.36. So therefore change in EK would be 30.72 minus 15.36. So 30.72 minus 15.36 is 15.36 itself. So we will say that this is just 50 joules. Okay, the collision in B lasts for 2 milliseconds. Assume that the contact force between the balls is constant during this time. Determine the magnitude and direction of the force exerted on ball X by ball Y during the collision. Okay, so remember, whenever the bodies are colliding, so for example X is colliding with Y, they both are exerting forces on each other. So Y is exerting a force this way and X is exerting a force this way. And the change in momentum for X would also be in this direction, and change in momentum for Y would be in towards the right also. So whatever the force is, change in momentum will also be in that direction. Acceleration will also be in that direction. So ball X, the force on ball X is towards the left. We need to find the force. So force is equal to rate of change of momentum. So mass is 240 10 raised to power minus 3. V is 0, right? And the speed before was 16, and time is 2 milliseconds, so 2 10 raised to power minus 3. So the minus 3 component will get cancelled. You have 240 times by 16 divided by 2, you get minus 1920. So basically the minus component already shows you that this is in the opposite direction. So 1900, two significant figures, and towards the left. Compare the magnitude and direction of the force exerted on ball Y by ball X during the collision with answers. So basically the force would be the same because they're action-reaction pair, Newton's third law pair, but direction would be opposite. So the magnitude is same, but direction opposite. That is towards right, because these two forces are action-reaction pair, or you can also say Newton's third law pair. That's it. Alright, that's it for question number 2. Moving on to question number 3. Question number 3. State the principle of moments. So this is also easy, that the sum of moments about any point is 0, but for an object in rotational equilibrium. For an object in rotational equilibrium, the algebraic sum of moments about any point is 0. You can also say for an object in rotational equilibrium, the clockwise moments about any point is equal to the anti-clockwise moments about the same point. Okay, a rigid uniform beam rests on the pivot at its center. So it's a uniform beam, so that means the weight would have been acting at this point. So considering the pivot, the weight will have no moment. A load of weight 2.6 Newton is suspended from the beam at a distance x from the pivot. A wooden cylinder of weight 4 newtons is suspended from the beam at a distance of 0.4 meters from the pivot on the opposite side of the pivot to the load. The cylinder rests in a container of water. The lower part of the cylinder is immersed in water to depth h. Initially, h is equal to 0.1 meters and x is equal to 0.4 meters. Okay, the system is in equilibrium. So if the system is in equilibrium, we can use principle of moments. Okay, use the principle of moments to show that the upthrust U exerted by the water on the cylinder is 1.4. Okay, so if we draw a free body diagram for the cylinder, you have weight acting on this and tension and upthrust upwards. So since this is we need to know what the tension is, because the tension is the one that's causing the moments over here. So and that's what we need. Okay, so wait, 2.6 times by x equals to tension times by 0.4, right? X is initially 0.4, no, wait, x is, x is equal to, right, okay, so we were right about this, 0.4, which means that tension at the moment is 0.4. Now we write this, that weight is equal to tension is equal to weight minus upthrust. So upthrust would be weight minus tension. Weight is 2.6. Weight is 2.6. Wait, what did we do wrong over here? 4 Newton, sorry, yes, weight is 4 Newton minus 2.6, and this will indeed come out to be for 1.4 newtons. So 4 minus 2.6, yes, 1.4 newtons. Simple math over here. Okay, moving on. The density of the water is 110 raised to the power 3 kilogram per meter cube. Calculate the area A of the cross section of the cylinder. So we have the upthrust and we also have, okay, so basically the volume that's displaced will be due to this h. So volume displaced, so volume displaced is AH, which is A times by 0.1, was it? 0.1 meters, okay. V volume displaced, okay. So upthrust is rho GV. Rho is 110 raised to power 3. G is 9.81. V is A times by H, which is 0. Wait a second, 0.1? Yeah, okay, 1. And upthrust was 1.4. So A would come out to be 1.4 divided by 10 raised to power 3, 9.81 times by 0.1. So 1.4 divided by 1000 divided by 9.8 divided by 0.1. So we get 0.0014 meter squared. Right, okay. And right here. More water is gradually added to the container in B, so that the depth h gradually increases. The length x is continuously adjusted so that the system remains in equilibrium. Okay. On figure 3.2, sketch the variation of x with h. Use the space below for any working. Okay, so basically remember that tension is the weight minus upthrust. So let's make it this way. So let's make a straight line equation. So 2.6x is equal to weight minus upthrust. What was it? What do we call this length? 0.4. And weight is constant, 4 times by 0.4, and minus upthrust rho G A H times by 0.4 also. Now we need to know what happens when x becomes 0. Okay, because we have already 1 point. We know that when x is when h is 0.1, x is 0.4. Right? This is what we have over here now. Let's point out. We already have this point over here. H is 0.1 and x is 0.4. So we have at least 1 point over here. That is this one. Now we need to know what happens when x becomes 0. So when x becomes 0, this side would become 0. So 4 times by 0.4 equals to rho GAH times by h. So rho is density of the water, 10 raised to power 3. G is 9.81. A we found out to be 0.0014 times by 0.4 times by h. So 0.4 gets cancelled. So h would be 4 divided by 1000 divided by 9.81 divided by 0.0014. Oh, sorry. 4 divided by 1000 divided by 9.81 divided by 0.0014, and yeah, 0.291 or 0.29. So we need to know where 0.29 is. So 0.29 would be over here, because you see 6, 7, 8, 9. So we have our 2 points. From this to this. Notice that this is not the y-axis, so this is not the y-intercept. So this point is not the y-intercept. You can draw a straight, you can make a straight line expression also, but remember this point itself is not our y-intercept. Okay, alright, so this is it for this question. Let's move on to the next one. Okay, so question number 4. Define stress, and the next one is strain. So these are easy. Stress is force per unit perpendicular cross-section area. So force per unit cross-sectional area. Oh, sorry. Oh, you can write it as perpendicular to the force. And strain is the ratio of extension to the original or unstretched length. That's it. Okay. Two wires X and Y with equal unstretched lengths of 0.84 meters are suspended from fixed points that are at the same horizontal level. Lower ends of the wires are attached to a beam of negligible mass. Beam is horizontal and is in equilibrium. Now this is a very important point. Wire X is made from a metal that has a Young modulus of this, and wire Y is made from a different metal. That means Young modulus of wire Y would be different. A load of weight 18 Newton is suspended from the beam at a point that is equidistant from the two wires. This load causes both wires to extend by 0.47 millimeters. Okay, determine the cross-sectional area of X. Okay, at some point we will need the forces in the wire X and wire Y. So how do we decide which one is what size are those? So we know that the object is in equilibrium, so we need to apply two conditions. Sum of forces in any direction is 0, so this must mean that Fx plus f of y equals to 18. And since the sum of moments about any point is also 0, so for example you can take this point, and they also said that it is equidistant from two wires. So for example, if we take this to be the pivot, if there are no and let's say this is x, this is x, although we don't have to take x, x is going to be something else, but f of x equals to f of y times by x, so this must mean that both of these are equal. So if both of these are equal, so this means that f of x equals to f of y, that is 9 newtons. Now this simplifies things quite a lot. So we know the Young modulus is FLAX, so we need A, which would be FL, EX. F is now 9 newtons. Original length is 0.84 meters divided by Young modulus, which is 1.9 10 raised to the power 9, and the extension is, I think this was in millimeters, yes, 47 millimeters. So 0.47 10 raised to the power minus 3. So obviously we need it in meters. So 9 times by 0.84 divided by 1.9 divided by 0.47 times by 10 raised to the power minus 9 plus 3. So we get a very long number. So let's turn it into standard form. This is 8.466 10 raised to the power minus 6, and that would turn into, for example, 8.5 10 raised to the power minus 6. meters squared. Okay. Wire Y has a greater diameter than wire X. That would mean that the cross-sectional area of Y would be greater than that of X. Explain without calculation whether the Young modulus of the metal from which the wire is made is less than, same, or greater than that. Okay. Now, Young modulus. Let's compare the Young modulus without any calculation. That means we don't need any numerical values, so we can compare these two. So we know, generally speaking, that E is proportional to F and L and inversely proportional to A and X. Now all the other quantities are constant. Force is constant, original unstretched length is constant, extension even is constant. So only thing that's left is inversely proportional to cross-sectional area. So basically we can say that since force, unstretched length, and extension are same for both wires, this means Young's modulus or Young modulus is inversely proportional to area A. So if the area of Y is greater, that must mean Young modulus is smaller. So area A of wire Y is greater, so Young modulus of Y is lower than that of X. Simple, straightforward. And this is the end of this question also. Now let's move on to the next one. Question number 5. A stationary wave is formed on a string XY that has a length 0.48 meters. Figure 5.1 shows the string at one instant in time. Speed of the wave on the string is 1400 meters per second. On figure 5.1, draw a cross at one position, that is node, and another that is cross at one position, that is an antinode. Okay, so this is a node, this is a node, this is a node, this is a node, and this is an antinode, this is an antinode, this is an antinode. Right, okay. Show that the wavelength of the wave produced is this. Okay, so wavelength is V over F. Do we have frequency? We have length. Oh, we don't have frequency yet, so we have to first deduce that. Explain your reasoning. Okay. Alright. So length. So length is, the total length is 0.48, and that is equal to, see, node to node is half wavelength, another node to node is half wavelength, this is half wavelength. So basically it's 3 by 2 wavelength. So length is 3 by 2 wavelength. So explain your reasoning. The length of wire string is equal to 3 by 2 wavelength times by wavelength of wavelength, since every node to node distance is lambda by 2, or half the wavelength. So lambda would be therefore 2L over 3. So 2 times by 0.48, yeah, 48 over 3. So 2 times by 0.48 divided by 3, so this is 0.32 meters. Okay, alright. Calculate the frequency of the wave. Now we can calculate the frequency, lambda. So V is 1400, lambda is 0.32. So 1400 divided by 0.32 is 4.375, 10 raised to power 3. So basically 4400. 4375. So 4400. Okay. A source of sound waves of frequency 780 Hz is on a rotating platform. Okay, the speed of the source is 39 meters per second. Sound is detected by an observer that is at large distance from the rotating platform as shown. Speed of the sound in the air is 320 meters per second. Calculate the maximum frequency of the sound detected by observer. Right. Okay. Maximum frequency would be, we can use the formula for Doppler effect. That would be observed frequency is equal to speed divided by speed of sound, V minus V source times by original frequency. So this would be, speed of sound is, 320 divided by 320 minus 39 times by frequency of sound wave 780. So that would be 320 times by 780 divided by 320 minus 39. This would be 0.0014. Wait a second. No. This was time. Oh, okay. Alright. So this is 888. So roughly 890 Hertz. Okay. At time t is equal to 0, the observer detects the sound emitted by the source when it was in the position shown in figure 5.2. On figure 5.3, sketch the variation with t of the frequency of the sound detected by the observer for one complete rotation of the platform. Calculations are not required. Now, to understand this, you have to know a little bit about simple harmonic motion, or a little bit about circular motion at least. However, that's not necessary, but we can still explain it because it's still part of A levels. Now, if you think of this point to be part of this circle, so let's say this is the middle, for example. This is not the middle, but alright, okay. And let's say this is this point at this point. Okay, let's say this is this point that is moving over here. Now, from the perspective, because it's oscillating about the center, so how do we quantify the relative velocity between observer and the source of the sound? So relative velocity is between the observer and the sound. So relative velocity between source and sound, observer, sorry, is actually this way, in this direction. not perpendicular. So we are interested in how the source of the sound, the displacement and velocity is changing with respect to this center. So if we can make it to be a circle of, let's say for example, this is the radius from the center of the circle. So, and let's say this is theta. So this particular displacement, let's call it, let's use a different color, r sine theta. Sorry, r sine theta. And this one would be r cos theta. So this is the displacement that we are interested in, the horizontal one, because this is the one that's changing here and there, because notice that this would be the horizontal displacement necessary for us to study. Now, if horizontal displacement is given by r cos theta, see we are starting our displacement over here, so it's starting with theta is equal to 0. That means it's starting at maximum horizontal displacement from the center. And if this is the displacement, let's call it x over here, so we know velocity, because we are interested in velocity. Velocity is the derivative of, displacement. So the derivative of cosine is, we already know, minus sine theta. It would be minus, technically it would be minus r sine theta. So either way, this is a sine cosine function. So the object's horizontal velocity is actually going back and forth like this, and velocity, relative velocity, is oscillating this way. So this will be exactly how the maximum and minimum frequency will be changing also. So there is going to be a maximum frequency, a minimum non-zero frequency. For the frequency, although we wrote this function as minus r sine theta, which basically means that this is going to be like this, we can actually see this on the platform also. So at this point, the horizontal velocity is lowest. At point over here or at point over here, they are going to be maximum, velocity maximum. However, since at this point it's going away from the observer, so velocity would be minimum. So velocity max, but frequency minimum. At this point, again, velocity is 0, so frequency would be 0. Not 0, but back to the original one. And because we have f naught is equal to v over v minus vs, so if vs even becomes 0, so this would, v over v would become 1, and this would actually become f naught is equal to f. So if stationary, source is temporarily stationary, f is equal to, f naught is equal to f naught is equal to f, and this point is moving towards the observer. So this would be where, and the horizontal velocity, so the relative velocity, is the maximum at this point towards the observer. So this would be the max. So since it is moving this way, so 0 minimum, 0, mean we can say, and maximum. So it's oscillating between this. So we will actually have f naught also. Let's call it f naught. Sorry, we can we will write it later on. So this would go this way. Now we can label them. This is your f max, f minimum, and f naught. sorry, source frequency, where f max is maximum observed frequency, f minimum is minimum observed frequency, and fs is the source frequency. Okay, alright, so this is the end of this question. Moving on to the next one. Define resistance. So resistance between 2 points is basically the potential difference, ratio of potential difference to the current flowing through them. So resistance is the ratio of potential difference between 2 points to the current flowing through them. Right, okay. A cylindrical metal wire of length 2.4 meters and cross-sectional area this has a resistance of this. There is a current in the wire of 4.7 amps. Determine the resistivity of the metal from which the wire is made. So we know resistance is rho L over A. So therefore rho would be R A over L. So resistance is 0.33. Cross-sectional area is 8 10 raised to the power minus 6. Length is 2.4. So 0.33 times by 8 divided by 2.4 times by 10 raised to the power minus 6. So this is, let's turn it into standard form. 1.1 10 raised to the power minus 6. So 1.1 10 raised to the power minus 6 ohm meter. Calculate the charge that passes through the wire in a time of this. Okay, so right. So charge would be, we know that Q is equal to IT. I passing through this is 4.7 and 5 minutes is 5 times 5, 60 seconds. So 4.7 times by 5 times by 60 is 1.41 10 raised to the power 3. So 1.4 10 raised to the power 3 coulombs, or 1400 also. The free electrons charge carriers in the wire have an average drift speed of 0.16 millimeter per second. Determine the number density of the charge carriers in the metal. Okay. Okay, so we have the formula I equals to NaQV. It could be NaEV also, depending on how we want it, because these are free electrons, so fundamental charge E can be used directly. We need to find this N over here because we have cross-sectional area, we have the fundamental charge, and we have the drift speed in millimeter per second also. So we need number density I over A EV. So I is 4.7 amps divided by cross-sectional area is 8 10 raised to the power 6, sorry, minus 6. E fundamental charge is 1.6 10 raised to the power minus 19 coulombs, and the velocity is 0.16 millimeter per second, so you need to convert it into meters. So 4.7 divided by 8 divided by 1.6 divided by 0.16 times by 10 raised to the power 6. Oh no, sorry. 6 plus 19 plus 3. So 2.28 29, sorry, 10 raised to the power 28. So 2.3 10 raised to the power 20. Okay. The wire in B may be considered to be a fixed resistor. It is connected in series with a thermistor to a battery that has negligible internal resistance. Use the wait. It is connected in series with the thermistor to a battery that has negligible internal resistance. Use the circuit symbols to complete figure 6.1 to show the circuit diagram for this arrangement. So remember, it can be modeled as a resistor. So you have a resistor, and we know what the symbol of thermistor. So thermistor is with a line sort of like this, and if you don't know, go through the symbols list in the book A-level syllabus booklet. We need to connect them in series. So this line connected with this line, this, and right over here. So right, that's it. We can label them also. So this is your fixed resistor or wire basically, and this is your thermistor. Okay, explain without calculation how the power dissipated in the wire changes as the temperature of the thermistor is increased. Okay, so if the T is in temperature is increased, the resistance of the thermistor would decrease, meaning the effective resistance of the circuit would decrease. If that decreases, the current would increase. So since the current flowing through the battery, the resistor and thermistor is increased, so the power is basically I squared R, so that would change. It can also be written as VI, power dissipated in the wire. So the power dissipated in the wire is not changing. The resistance of the wire is not changing. The current flowing through it, however, changes. So the power dissipated would increase. So we need to be able to explain this, that as temperature increases, resistance of thermistor decreases. This causes net resistance of circuit to decrease, causing current flowing through the circuit to increase. Since current flowing through the wire has increased, since current flowing through wire increases without any change to its resistance, power dissipation would increase as power dissipated is proportional to square of the current. That's it. Okay, and this is for this question number 6. Let's move on to question number 7. Question number 7. Complete table 7.1 to show the charges in terms of elementary charge E on each of the flavors. So up, down. Remember, we also can see this in the booklet. Let's show you the booklet. So this is the grade definitions and formulae booklet, which, as you can see, the link on the grade booster pack on Patreon. The link you see below will have this. So we go to particle physics, and there is a table of particle physics. Yeah, this one. Okay. So you see, up, charm, top have the same charge, plus 2 over 3e. Down, strange, bottom have minus 1/3 e charge. So you should be able to memorize these easily, and if you want any help, definitely you can go through the Patreon link to buy the grade booster pack. So coming back to the paper, we have up, charge, it's a quark. None of these are anti-quark. Wait a second. Up and okay, so we basically need the charges on the anti-quark first. So up quark has plus 2/3 e, and anti-quark will have minus 2/3 e. Down will have minus 1/3 e. Sorry, we don't need e. And up anti-quark, down anti-quark would have plus 1/3 e. Strange, it has the same magnitude of charge, so 1/3 e would be the answer. Right. Okay. Right. State the name of the class or group of fundamental particles to which baryons and mesons belong. Hadrons. It's basically not the fundamental particles themselves, but the hadrons are built on top of quarks. Okay. Compare baryons and mesons in terms of their constituent particles. So also you can see this in the grade booster pack. See this. Baryons are made up of 3 quarks, but mesons are made of a quark and an anti-quark. Okay, so that's basically what we need to know. So either they're made of 3 quarks or 3 anti-quarks also, but mesons are a quark and an anti-quark relationship. So baryons are composed of 3 quarks, while mesons are composed of a quark and an anti-quark. That's it. Describe beta plus decay in terms of the fundamental particles involved. Okay, so we know that in beta plus decay, a proton decays into a neutron plus beta plus particle and an electron neutrino. But what changes happens in proton and neutron? So a proton is up, up, down, and neutron is up, down, down. So the basic change is that one up is converted into one down, plus one beta plus particle, plus one electron neutrino. And you can see this over here also in the same document, Definitions and Formulae booklet. The beta plus decay equation for quark level changes, up converts to down plus beta plus plus electron neutrino. So that's what we need to describe over here. So an up quark changes to a down quark and results in emission of a positron, beta positive particle, and an electron neutrino. And basically this is it. Hope you like this video. If you have any questions, doubts, or confusions, feel free to reach out in the comments. I would love to help you out. Do check out the Grade Booster Pack on Patreon. The link is given below. It has the components from A2 and AS. Both of them you must have seen me using in paper 4 papers also. So meanwhile, take care of yourself. Hopefully we will see you in the next video. Bye bye. Take care.